Julia,
Alexis,
and Tiffany.
So today we're going to be explaining the physics behind bungee jumping.
So if you've ever wondered how the physics behind bungee jumping works,
well, you're about to find out!
Yeah!
First, we're going to break bungee jumping down into 3 intervals.
The first interval is when the jumper's bungee cord has not yet been stretched.
The second interval is when the bungee cord begins to stretch and the jumper slows down.
The third interval is when the jumper accelerates upwards and oscillates until he or she reaches a stop.
In the first interval, the jumper experiences free fall. Gravity is the only force acting on the jumper and the bungee cord is relaxed. Due to the acceleration of gravity, the jumper falls at a constant rate of negative 9.8 meters per second squared.
In the second interval of bungee jumping, the bungee cord starts to stretch, and the force of tension starts acting on the jumper. The farther the cord is stretched, the more amount of tension there is. As the tension increases, the acceleration goes in the upward direction. But since the jumper is still falling in the downward direction, and the velocity is still in the downward direction, this means the jumper slows down. When the force of tension becomes greater than the force of gravity, there is a non-constant force, which causes a non-constant acceleration.
In the third interval, the bungee cord stretches to its maximum length. The strong force of tension that has become greater than the force of gravity causes an upward acceleration for the jumper. But before the jumper is pulled up, the jumper's velocity is at 0. The jumper then oscillates or swings up and down until it reaches a stop. This happens due to air resistance, which causes gravitational potential energy to be lost. Also a fun fact, in bungee jumping, in theory, air resistance cannot be neglected because if there was no air resistance, the jumper would oscillate to the same height forever. For example, if there was no air resistance, the graph of the motion of the jumper would look like this, oscillating to the same height persistently forever. But in real life, with air resistance, the graph of the motion of the jumper would look like this, with the jumper losing gravitational potential energy with every oscillation back upwards.
Second interval, as the cord begins to stretch, Hooke's law starts applying to the situation. Hooke's law states that the spring force of a spring, or the force that restores the spring back to equilibrium, is equal to the negative product of the spring constant and the displacement from equilibrium. The negative sign signifies that the direction of the spring force is always opposite of the direction of the mass's displacement from equilibrium. Every spring has a different spring constant. In bungee jumping, choosing the spring with the appropriate spring constant is crucial for jumpers of different masses. If the spring constant is too low, the jumper will oscillate too much and could hit the bottom of the river. On the other hand, if the spring constant is too high, the jumper will not experience the full exhilarating experience of bungee jumping.
Now we're going to talk about the energy throughout the jump for bungee jumping. As the jumper stands on the platform, the gravitational potential energy is at its maximum. Kinetic energy is 0 because the equation for kinetic energy is 1/2 mass times velocity squared. And since there's no motion, there's no velocity, which means kinetic energy is at 0. Elastic energy is also at 0 because the equation for elastic energy is 1/2 mass times spring constant squared. And since the cord is not stretched, displacement from equilibrium is 0, and therefore elastic energy is also at 0.
The equilibrium point is the point where, once passed, the cord begins to stretch. When the jumper falls to this point, some gravitational potential energy is lost, and the lost gravitational potential energy is converted to kinetic energy. Elastic energy is still at 0 because the cord has not stretched yet.
As the jumper continues to fall, the jumper reaches maximum speed. At this point, more gravitational potential energy is lost and kinetic energy is at its maximum. This time, however, the gravitational potential energy lost is not all completely converted to kinetic energy. Some of it is also converted to elastic energy since the cord has now stretched. Then, the jumper falls to the most bottom point of the jump, where velocity is at 0. Here, the gravitational potential energy and kinetic energy are at 0, and all the energy is converted to elastic energy. Afterwards, the elastic energy tries to fling the jumper back to the equilibrium point repeatedly, but the jumper slowly loses height due to air resistance and eventually stops at the bottom point of the jump again and ceases to move.
Okay, so that's all we have for you today. Thanks for watching the video, and we hope you enjoyed it.
And if you did, remember to give it a big thumbs up and subscribe down below.
See you